Have NMR, mass spec, and infrared data. So it's good practice. Let's just make sure we all know how to do this. Our first compound, C3H6O, molecular weight of 58. This is this mass spec. First thing we always want to do is degrees of unsaturation. If we had 3 carbons, we should have 8 hydrogens. We only have 6. Remember, we ignore the oxygen, so we have 1 degree of unsaturation. Either a carbonyl, a double bond, or a ring. 3 carbons, probably not a ring. Most likely a carbonyl would be a good guess. All right, next, let's look at the mass spec. Now, we're given that the molecular weight is 58. And sure enough, right here we have a molecular ion at 58. On an exam or something, I would probably write down M plus at M/E 58. We also have a peak here at 43. Now remember, 43 is a very common fragment. It either represents the acylium ion or a isopropyl or 2-propyl carbocation. They both weigh 43. So we have a nice peak at 43, and this is M minus 15. So this is loss of a methyl group. So what you might say is base peak at 43, loss of a methyl group, could be an acylium ion. Any questions so far? All right, next we want to look at the infrared. Oh, a very nice infrared. On an exam, what I'd like you to do is to take and just step through the standard bands and put down either, yes, we have an absorbance, or no, we don't, blah, blah, blah. So, starting up here at 3400, we have that little tiny blip there at 3400, but clearly that's not an OH peak. Remember that they are big and broad, very intense. So no OH. Look at the high side of 3000. Nothing there. Probably no sp squared CH. Just below 3000, we have a nice peak. We have saturated or sp cubed CH. We have nothing here in the triple bond region, but we have a beautiful fat carbonyl here at about 1710. In the 1600 range, we don't have anything to suggest a double bond. The carbonyl here and this MOE of 43 really suggests that we have an acylium ion. Any questions? All right, we have C13 data, and we have proton NMR. Our proton NMR here shows 1 peak. Because it's 1 peak, we don't have an integration. Remember, they're relative areas. But this tells us that all of the hydrogens are equivalent, and that no carbon bearing a hydrogen is adjacent to another carbon bearing a hydrogen. So they're isolated methyl groups. Singlet at 2.1, we'll say 6 hydrogen, because that's what we have. 2 isolated methyl groups. It's shifted up here a bit to 2-ish, so there's something mildly electronegative next to it. Now our C13, we have a singlet at 206. Remember at the 200s, that's where you get aldehydes and ketones. An aldehyde would give us a doublet, wouldn't it? Because we have hydrogen directly attached to that carbon. This is a singlet, so this tells us it's a ketone. Finally, we have a quartet down here at 27-ish. That means it's a CH3. And even though we have 2 carbons to deal with, they're identical. So we could say ketone carbonyl, methyl groups, again, mildly electronegative. Yeah.
So when you don't have that labeled singlet and quartet, how do I identify this on here?
What, identify what?
Like, is it one of these lines or?
This, you mean?
Yes. How do I identify? Because you know, like for the lab, we had all these lines and everything. How
Right.
do I identify this?
Well, see, this just avoids having to print the spectrum, frankly. This says we have a peak here at 27 parts per million. And when you allow proton coupling, that's a quartet.
But there's not, there is, I think what she's saying is there isn't 4 peaks on that graph, so is it correlating to that, or no?
Well, because both of our methyl groups here must be identical. So because they're both identical, they just show up as 1 peak here and 1 peak here.
Okay, so that's
So we put all this stuff together. This is our acylium ion. Remember, acylium is a methyl group bonded to a carbon triple bond oxygen. It's a positive fragment, very common whenever you have carbonyl and a methyl group attached. We know we have 2 methyl groups, and they must be identical. Frankly, with 3 carbons, there's only one way you can put it together, and that's to make acetone.
I had a question about this one. The graph that we just saw, wasn't that the 1H?
Right.
And so you don't even show the 13C graph at all. You just
Just
give
give you the data.
the data. Is that what's usually going to be? Like,
That's the way it'll be on the exam.
Okay.
The problem with showing a C13, even though I did it for the other, the problem with showing that is that, remember you run a proton couple first. And that's how you get quartets and doublets and singlets and stuff like that. Then you turn on the decoupler and you get nice intense peaks, but the intensity is not proportional to the number of carbons. So it doesn't tell you much except the chemical shifts. So most people will just give data as opposed to actually showing the spectrum, because you never know which one to show. Compound number 2. C2H5I. How many degrees of unsaturation here? Well, we have to remember our rule. A halogen is just like a hydrogen, isn't it? So this is the molar equivalent of C2H6. And that means no degrees of unsaturation. We have an iodine in here, so let's don't forget that guy. And only 2 carbons to work with. Here we have the molecular weight is 156, and we have a nice molecular ion here, also at 156. We lose a chunk here. How much is that?
29.
Yeah, minus 29. What weighs 29? Well, 2 carbons and 5 hydrogens, an ethyl group. Methyl is 15, ethyl is 29. So we could say loss of an ethyl, and we have a nice clean molecular ion at 156. Our infrared. Do this the same way. Start up here at 3400. There's nothing. 3,100, still nothing. Nice peak at about 2,900. We have no triple bond peak. We have no carbonyl. And we have nothing at 1,600 for double bonds. This is nothing but saturated carbon. And of course, we know we have an iodine.
I had a question about the last slide. Why did you have M over E equals 29, 80%? Are you trying to show that we, like, for the last?
Okay, I don't remember. Did you say 20%?
80%.
Oh,
And,
see, this is another peak that's off scale here.
oh, okay.
Because this only went down to 30, and there's another peak at 29. That's what's left of our ethyl group.
That,
Again, the ethyl weight is 29.
that, I guess I'm just.
So if I would have taken this down to 0, we'd have another.
So we'd have another peak. Okay.
The graph looks different than what you've shown us before, so the highest number, that's always going to be our molecular ion.
Pretty much. All right, let's look at our NMR data. Proton NMR, we have a quartet and we have a triplet. Remember, whenever you see a quartet and a triplet, especially if they seem to be leaning towards each other, you say to yourself, that is an ethyl group. The CH2 here is shifted up to around 3-ish, so it's next to something electronegative. Our C13, we have a quartet and a triplet also. This is very low, this is shifted up a bit. Again, this is a CH3, a CH2. This again is very, very low. All right, so we would say this looks like a simple ethyl group. Finally, if we put our pieces together, we have an ethyl group. That's about it. And we have an iodine in our molecule. This must be ethyl iodide. Any questions? Number 3, C6H12, molecular weight 84. If we had 6 carbons, we should have how many hydrogens? 14. So we have 1 degree of unsaturation. If we look at the mass spec, we see we have a little molecular ion here. I would note that. We have an M minus 15, give us a peak at 69. We also have something at 41. I don't know what that is. In spectroscopy, it's okay to say that. Just don't say it too often. We don't know what 41 is, but how far away is it from 84? It's 43, isn't it? So this is an M minus 43. I told you these are very common. So our molecular ion is losing either an exilium ion or a 2-propyl group. We don't have an oxygen, so it's a 2-propyl carbocation. So what we can say here, we have loss of a methyl and loss of isopropyl. Everyone happy with that? As to exactly what 41 is, I don't have a clue. But we know how it got there. Infrared. Do our usual. We'll start here at 3400, and there's nothing. Nice little sharp peak here at about 3100. That would be consistent with sp squared CH. Really nice big peak at 2900. We have no triple bonds. Here at 17, we have no carbonyl. At 16, actually it's a little bit high, about 1640 or so. Looks like we have a very nice carbon-carbon double bond stretch. Our conclusion, we have an alkene based on that, and one DU. And that's about it, and a lot of CHs. Any questions? NMR. All right, our proton NMR. We have two areas here. We have one nice big peak with 9 hydrogens. They're all the same. This is 3 identical methyl groups. Okay, and they're all the same. They are not adjacent to anything with a hydrogen. Okay, so they're isolated and they're all the same. Down here in the region 5 to 6, we have 2 multiplets, really. You could look at the multiplets and you could actually diagnose a splitting pattern, but we're not going to do that right now. This is worth a total of 3 hydrogens, and this is the region of the spectrum where we get absorbance from hydrogens attached to double bonds. So we have probably a CH, CH2. They're both attached to double bonds. This is one, this is a CH2. So it looks like we have this fragment and we have 3 identical methyls. All right?
How can you tell that there are 3 of them?
Well, it's 9 hydrogens.
Oh,
9 times 3, or sorry, 3 times 3 is 9. All right, RC13. Well, let's see. Start down here. We have a carbon that's a quartet. So that's a CH3, isn't it? Well, we already know that we have 3 CH3s. We have a singlet. So that's a carbon with no hydrogens attached. None. We have a doublet and a triplet, just like these guys. So this is a CH and a CH2. These are shifted down to where we get double bond carbons, sp squared carbons. So our conclusion, simple methyl group, that's this guy, doublet and triplet in the alkene region, and 1 isolated carbon with no hydrogens. So if we put our pieces together, we have 3 identical methyls. We have one carbon with nothing attached, no hydrogens attached. And we have a double bond, or CH-CH2. Only way to string these together is to make that. 3 identical methyls, 1 carbon with nothing attached, no hydrogens, CH-CH2. Number 4. C7H14.
The exams will be multiple
That's
choice,
16.
Dr. Young?
Sorry?
The exams will be multiple choice?
Oh, you're so funny. We have 1 degree of unsaturation. If we look here, we see again our familiar friend at 43. That's either a psyllium or isopropyl. We have our molecular ion, 114 minus 43 is what? 71. So I don't know what 71 is, but this is loss of 43. And here's the 43. So we either have a psyllium or we could have isopropyl. We don't know yet. Everyone happy with this? All right, infrared. 3400, we have no OH peak. 2900, I don't see much there. 3100, I'm sorry. 3100 with nothing. 2900, we have a very, very nice large peak, several of them actually. We have no triple bonds, and we have a beautiful carbonyl here at 1710. We have nothing here that would suggest carbon-carbon double bonds. So it looks like a nice, simple, aliphatic ketone. We know it's not an aldehyde, don't we? We didn't put this in our list, but if this was an aldehyde, at 2750 right here, we would have a nice doublet. We'd have 2 peaks. So we know it's not an aldehyde. And our proton NMR, by George, we have a doublet. And if you count these little guys, you get 1, 2, 3, 4, 5, 6, 7. It's a septet. This is worth 6 hydrogens. This is worth 1. This is an isopropyl group, isn't it? 2 identical methyls attached to a CH. Any questions? Our C13, we have a singlet at 214. That is a ketone carbonyl. Remember, if it was an aldehyde, it would be a doublet. So it's a ketone carbonyl. We have a doublet and a quartet. So this is a CH and a CH3. That means that all of these guys must be equivalent. because we have 7 carbons to work with. So we have lots of redundancy, lots of symmetry in our molecule. So what we know, we have a CH, a CH3, and a ketone carbonyl. Putting it all together, our peak at 43 could be a psyllium or isopropyl. We don't know which. There is a carbonyl though. If we had a psyllium being formed, we would expect a peak from this methyl group, wouldn't we? A singlet or 3. And we don't see that anywhere. Therefore, this is not a psyllium. This M-43 is isopropyl. So, we know we have a ketone. So start off with a ketone. We are then missing 6 carbons. And they're all the same. We have 2 isopropyl groups bonded to our carbonyl. All we see is isopropyl because they're identical. And of course, our ketone carbonyl.
So when you said that you didn't know what the 43 was, does that mean that you just don't know what you're left with?
Well, we don't know if we've lost a psyllium or if we've lost isopropyl. Could be either one. But when we looked at the NMR did not show us an isolated methyl, did it? So we don't have a psyllium. So all the 43s must be isopropyl.
So did we lose 43 twice?
Was it M43?
Yeah.
Is it supposed to be lost at M43 instead of peak?
Well, we had a peak at M43 and we also had a loss of 43. So we had both.
That was what was the confusing part.
Okay. C7H5N. We have a nitrogen. Now remember when we do degrees of unsaturation with a nitrogen in our compound. Nitrogen is bonded to 3 things. Carbon to 4. Therefore, when we have a nitrogen and we're doing DUs, we need to subtract 1 hydrogen for every nitrogen. That's just a rule. So this gives us 6 degrees of unsaturation. Now, whenever we have more than 4 or more, we really think about a benzene of some sort. And we also have 2 more degrees of unsaturation. When we look at our mass spec, we see a molecular ion. It's the base peak, highest peak. And we see an M-15. But that's it. Is that 15?
No.
No, what is that?
27? 27?
27, okay, that's true. M-27. Gee, what I would look at this and say is, I know I have a benzene ring here, and because I don't see a peak at 91, I don't have a benzyl group. Okay? If we had a benzyl group, we would have a peak at 91. So nice negative information here. M-27, I don't know what it is. But we don't have a benzyl. So let's look at the infrared. Starting at the top, 3400, we have nothing. Here at 2900, 3100, we have a nice sharp peak. So this is sp squared CH. 2900, we don't have anything at all. So we don't have any sp cubed CH. But look at this beautiful sharp peak here at about 2200. That is a triple bond stretch. In fact, it is so long, so good, so clean for a triple bond, this highly characteristic of a nitrile. Nitriles give the best triple bond stretch. Down here we have nothing for carbonyl. We have nothing, well, we have 1, 2, 3, kind of ugly peaks, but those would be consistent with a benzene carbon-carbon double bond. Would be consistent with, they're really not much to write home about. I might even say suggesting possible. So this looks like we have a benzene ring and a nitrile. NMR. We have a ragged sort of peak down here at about 7.5. This is where we have benzene hydrogens. We would suggest that this is consistent with our substituted benzene. If we look at the C13, remember we can use C13 to pick out substitution patterns on a benzene. If we had a monosubstituted benzene, we would expect a singlet and 3 doublets. So this singlet, these 3 doublets suggest monosubstituted benzene. We have one more singlet left, but remember from the IR we said it's probably a nitrile. That would be the nitrile carbon. Finally, if we put it together, we have a monosub-benzene, we have a triple bond. Oh, how about that? 27 is loss of HCN. Not something you often see, but HCN weighs 27. Now we can do that because we know the structure. This clearly is acetonitrile. Or benzonitrile, sorry. All right, our last one. C7H7Br. That's equivalent to C7H8, which means we have 4 degrees of unsaturation. Look at our mass spec. Down here, our molecular weight is shown as 71. We see 2 peaks, one at 70 and one at 72. And they're the same height. Well, that's not too surprising because remember bromine. We know it as a bromine. Bromine consists of 2 isotopes, equal quantities, and they're 2 mass units apart. So this is our molecular ion. Whenever you have a bromine in your molecule, you expect 2 ions, 2 units apart. The thing that stands out here is our big happy peak at 91. This should scream at you once again. This has a benzyl group. Remember, the peak itself is tropylium, but that's just a rearranged version of benzyl. For our NMR, Oh, we didn't do IR, did we? Sorry. 3400, they're nothing. 3100, nice peak for unsaturated CH. Nice little peak for saturated CH. No triple bond. No carbonyl. And we do have peaks here that would be consistent with benzene carbon-carbon double bonds. This looks like we have a simple benzene compound. If you look at these little guys here, this handful of peaks there, and these guys down there, remember we said those show up for monosub-benzenes. So it kind of suggests that. Doesn't prove it, but it suggests that. Proton NMR, we have two peaks. Down here in our benzene region, we're at 5 hydrogens. That's a monosub-benzene, isn't it? And we have an isolated CH2 that's shifted up to about 4-ish. So it's next to something electronegative. Our carbon. Again, we have a singlet and 3 doublets. That's a monosubstituted benzene. And we have a triplet, so that's a CH2 at 29. Again, that's just something mildly electronegative. Putting this all together, we have a benzyl unit, and we have an isolated CH2. We're missing a bromine. This clearly is benzyl bromide. Now, isn't this fun? The correct answer is, yeah, this is kind of fun.
It's kind of interesting.
It's not interesting.
Yeah.
It's problem solving. It's,
Strategy.
you know, you have all these data, you take the fragments, you put it together, you try to come up with something. Now, on the exams, remember, it's worth 25 points. And you only get 5 points if you get the structure right. So the 20 points come from just analyzing and saying the obvious, simple things from all the spectrum. All right. You want to take a little quick 5-minute break? And then we'll come back and we'll do conjugated dienes and cycloadditions.
Things were unplugged and we had to get them plugged back in, so IT came here and okay, let's see, maybe IT did that.
You got it. All right. Thank you so much, Terry.
Yeah.
I don't think it should. But even if I didn't, I think I would just probably say, I don't think we're taking any other classes because then it's sort of, are you gonna retake?
All right, let's go ahead and get started on chapter 14. Conjugated dienes and cycloadditions. When we talk about a conjugated diene, What we're actually talking about is a collection of sp squared centers that are adjacent to each other. An example here, this is the structure of retinol, of vitamin A. And if you look at the chain here, even starting in the ring, all of these carbons in a row are sp squared. So this forms one long conjugated system here, where all these double bonds and their pi systems overlap. Now, when we say they overlap, remember when we talk about a simple alkene, we said that a simple alkene, the double bond in an alkene, is formed by the p orbitals here on the adjacent sp squared carbons, and they overlap, and this makes what we refer to as our pi bond, our second bond, etc. When we have a conjugated system, each of these carbons will have p orbitals, and so these overlap like this to form a continuous pi system above and below the plane. Now, this is slightly different than the pi system here in a simple alkene. In a simple alkene, the barrier for rotation is really high. In a conjugated alkene, the barrier for rotation is much less, so we can take this single bond, if you will, so this one here, and we do have rotation. Now it's hindered, but it's much easier to rotate about that than it is a simple alkene. That will become important later. All right. If we want to make a conjugated diene, we already know a very simple way. We know that the allylic carbons in an alkene are very reactive towards free radical bromination. That's because the radical that you form here is very, very stable, resonance stabilized. Second step, we add Br dot, and we make this guy. Once we have that, we can do a simple E2 elimination, eliminate across here to make the conjugated diene. Again, the mechanism with NBS in carbon tet, we're going to generate bromine radicals. Bromine radical is going to pull a hydrogen atom off of here, and it's going to give the resonance stabilized allylic radical. Remember, we can take this radical by resonance, move it from here down to here, so we have radical character at both of these carbons. Once we have our radical character established, all that happens is Br dot is going to add here, get our product, and then once again we do elimination. Any questions? We did this back in 234. All right, if we have an alkene, and I say I'm going to react it with HBr, everybody remembers from way back in chapter 6 or whatever. What we're going to do is a stepwise addition. We're going to have a carbocation intermediate, and we're going to have Markovnikov regiochemistry. So let's just take one of these double bonds, these guys. We're going to add HBr. The most stable carbocation would be here at our secondary position. So that is where the bromine will add. Hydrogen goes here. Markovnikov's rule, carbon with the most hydrogens gets the hydrogen. My rule, You add the hydrogen to get the most stable carbocation. Now, because we have 4 carbons in our conjugated system here, what we've done is we've added HBr to carbons 1 and 2. We call this 1,2 addition. However, if you do this reaction, in addition to 1,2 addition, you also get 1,4 addition. That is, the hydrogen goes here, and the bromine at the other end of the molecule. So looking at our starting material, hydrogen here, bromine here. We get 1,2 and 1,4 addition. Now the mechanism for the 1,4 addition is actually very simple. Step 1, we're going to protonate this guy in order to get our most stable carbocation. So here, we added a proton, added the hydrogen here, and we get our secondary carbocation. We realize, of course, that the secondary carbocation is resonance stabilized. So we can move this electron pair in, like this, and we have carbocation character here. Now if you think about it, this tells us we have carbocation character at this carbon and this one. We could add bromine here to make 1,2, or add bromine here to make 1,4. If we simply take this position here, our position number 4, add our Br minus, we get the 1,4 addition product. So the reason we get 1,4 and 1,2 is the intermediate that you form is resonance stabilized. That means it has positive character at least 2 carbons along the chain. Addition here is 1,2, addition here is 1,4. All right. This has actually been studied a lot. Turns out that the 1,2 forms rapidly at lower temperatures. So if you wanted to make only 1,2, you would just run it for a little bit and keep your temperature fairly low. If we pump our temperature up, we're going to get 1,4. And if we take pure 1,2 and let it sit long enough, it all reverts to 1,4. Now what this tells us is that the formation of 1,2 is faster. That is, it has a lower activation energy. So this requires more energy to react. What this tells us is that the 1,4 is a more stable product. So when we finally get there, it stays. We can explain all of this using reaction coordinates. Started here with our diene, and let's make the 1,4 addition product, because we have to start somewhere. Now we know that the 1,2 forms faster. If it forms faster, the same starting point here, that means it must have a lower activation energy. It takes less energy to make it. So less energy to make it, lower activation energy, faster reactions. But we also know that the 1,4 is more stable than this guy. Therefore, the rest of the curve must look like this. This is faster, but this is more stable. This is how you use reaction coordinates to explain the dynamics and the product distribution. And again, if you really wanted to make 1,2, this would tell you you want to do it cold and fast. If you want to make 1,4, warm it up, let it sit. One, 2 is faster, 1,4 is more stable. Any questions?
Will the 1, 2 then eventually turn into?
Yep, it will.
Just every time?
What happens is, we're here, it's reversible. So we lose HBr, go back here, and then we slowly add this. Once we get here, it stays. So it all trickles down to the 1,4. When you have something gets formed faster, we call that the kinetic product. Kinetics, the study of reaction dynamics. Thermodynamics means it's slower, but it's more stable. So just nomenclature. Any questions? Very simple reaction. Let's go ahead and look at some examples. Take each of these. What I like to do is to look at them and say to myself, what is the most stable carbocation? Because that will tell you where the proton is going to add. Secondly, if we're doing 1, 2, all we have to do is add halogen to that carbocation. For the 1, 2 addition, look at this molecule. The most stable carbocation is going to be here at this tertiary center, isn't it? That means we're going to put the proton on here. And that is our carbocation. We put the proton here, positive charge here. Now to make the 1, 2 product, all we do is take Br minus, add it to the carbocation, and we get this. Any questions? Why think about the 1, 4? Where is the proton going to add? Well, exactly the same, isn't it? Exactly the same. We're going to form the same carbocation, just like we did. The only difference is this is resonance stabilized, isn't it? Well, they both are, but if we want to draw our resonance forms, we could move this double bond in, placing a positive charge out here. If bromine adds to carbon 2, we get this guy. If bromine adds to carbon 4, we get the 1, 4 addition product. So the 1, 4 product would simply look like this. Cyclohexadiene, gonna make a 1,2 addition product. Step one, you wanna look and figure out what's gonna be the most stable carbocation. Now they're all secondary carbons, aren't they? But if we had our carbocation up here, it would be isolated from this double bond and would not be resonance stabilized. So you get the most stable carbocation if we protonate here to form this, again, this resonance stabilized by this double bond. Another way to think of it, this is an allylic carbocation, much more stable. All right, so if this is our carbocation, all we have to do is add bromine, or Br- to this carbon, and that's our product. Now for 1,4, it's going to be the same thing all over again. We're going to protonate at the same place to make the same carbocation. But now we're going to add to the 4 position, which we can do because it is resonance stabilized. This would give us 1,2. This would give us 1,4. All we have to do is take our Br-, add it to this carbon, and we get the 1,4 addition product. Hydrogen here, bromine here, 1,4 addition product. Any questions? Now I hope you noticed that the 1,2 and the 1,4 are actually the same compound, aren't they? Different mechanisms to get there with the same compound. All right. The real point of chapter 14 is to talk about what's known as a conjugate addition, a cycloaddition reaction. This is also called the Diels-Alder reaction, after the 2 guys that developed it. It's also referred to as a 4+2 cycloaddition, or 4+2 electrocyclic reaction. All those refer to the same thing. In the Diels-Alder reaction, you're going to take a diene, so a conjugated system, and you're going to take an alkene. We're going to call that dienophile, something that loves dienes. They are going to react, and we're going to get a 6-membered ring containing 1 double bond. Diene and dienophile react to form a cyclic alkene. This happens this way. Here's our diene. Now you'll note that I have rotated my diene into what's called the S-cis configuration. So both double bonds are on the same side. Remember, we do have rotation possible around here. Takes a little bit of energy, but you can do it. And we get the S-cis configuration. Next, I'm going to bring my dienophile up to it. They're going to like bump into each other, say hello, and then, in one magical step, electrons are going to flow, double bond in here to make a bond, make a simple alkene, and we get this as our product. The bonds that we've made here are shown in red. This is the bond on the top, the bond on the bottom. 4 + 2 cycloaddition. 4 carbons, 2 carbons. Concerted reaction, no intermediate. All of these electrons fly around at once. Any questions? Now when you look at a cycloaddition reaction, it's important to be able to look at the product and figure out what the reactants were. Very simple way to do that, very simple rule. What you do is you find your double bond here. You look across the ring, across our 6-membered ring. These were the 2 carbons of our dienophile. These 4 carbons came from the diene, these 2 from the dienophile. All right. Here's a reaction we just looked at. Our diene is simply 1,4-butadiene. Ethene is our dienophile, and we make cyclohexene. These guys, there's our diene, there's our dienophile. In this molecule, those are the carbons. The diene and the dienophile. Look across your double bond, or across the ring from the double bond, to find the dienophile. How about this? What if we take cyclopentadiene and ethene? Well, what's going to happen is the same reaction. We're going to react from this carbon and this one with our dienophile. So this carbon's going to react here. This one's going to react here. When we do this, we're going to form a 6-membered ring. But remember that the 2 carbons here of our diene are linked together by a CH2. So they're still there, and they're still linked together. The product would look like this. This is our diene part. We're going to have a double bond now. These 2 carbons are linked by a CH2. This is the rest of our 6-membered ring. Color it. Here's the carbons of our diene, these guys, carbon of our dienophile. Look across the 6-membered ring to find the dienophile. Aren't you glad you practiced your work so much back in 234? So now you can draw structures like this and make them look beautiful, just like me. Let's take 1,3-butadiene and react it with this guy. Now this is actually a conjugated system itself, isn't it? We have p orbitals here and here. So this is a conjugated system too. In chapter 19, we'll talk about the moral equivalent of 1,4 additions to these guys. But right now, we're just going to use this as our dienophile. So what's going to happen? These terminal carbons are going to add here. These are the 4 carbons of our diene. This used to be our double bond, and this is all the rest. Any questions?
So in the
All right, let's talk.
Dr. Young,
Yeah.
on the exam, you're just gonna have examples of these and tell us the reproduce them?
I'm gonna
On
have
the,
what?
on the exam, you're just gonna have examples of these and just have us reproduce them?
Oh, yeah, sort of. And you'll see.
Okay.
As I said, in order for this reaction to occur, the diene has to be in the S-cis configuration. Now, this does require some energy. That's pretty much why you have to warm it up. Actually, most Diels-Alder reactions are done in what's known as a bomb. And like at USC, we had a dedicated bomb room. So with thick concrete walls, the ceiling was blowout. You had this, looked like a mortar. Put your stuff in there, seal it up, leave the room, turn it on, and it would go. And if it blew, it would just blow the ceiling out. But you need to heat it up in order to have the thing work. Why do we need the S-cis configuration? Well, it has to do with the actual mechanism of the electrocyclic reaction. Let's look at a very simple reaction here. Butadiene, we're in the S-cis, and we're reacting it with ethene. Now these are all double bonds, so they have p orbitals, don't they, for their pi system. For the diene, our p orbitals would look like this. We're going to react this with our dienophile. Now it also has p orbitals. And we'll draw them in like this. Now all of a sudden you can see how this works. These guys right here simply collapse to form a single bond. Same thing with these guys. These are leftover p orbitals, aren't they? Therefore, when we form our bonds, these guys, these are left as our alkene. These guys, again, simply convert to our single bonds. These are dienophile, and these are left over as our pi system. Any questions? All right, well, let's keep this image in mind. The thing that I'm going to point out here right now is that whatever stereochemistry we might have here on our alkene, that is our dienophile, is going to be preserved. It's going to be preserved because all of these bonds form simultaneously. Nothing happens that could change this stereochemistry. So let's look at an example here. Here I have a cis dienophile. These are nitrile groups attached to a double bond. Cis stereochemistry. Up here I have butadiene. This is my diene. Now, based on what we saw, we know that this carbon and this guy, this carbon and this guy, are going to join. Our p orbitals are going to leave a double bond back here. Now we show the process using these arrows, but again we realize that it's just these orbitals mixing. That's why it's electrocyclic, that's why it happens all at once. So when we're done, we've made a bond here and here, and this is now our double bond. All right, what I'd like to do is demonstrate that the stereochemistry here has been preserved. Now remember, we're making a 6-membered ring. Remember back in chapter 3 when we talked about cycloalkanes. We talked about axial and equatorial groups, stuff like that. Now, we're going to use this. Let's take this structure, and what I want to do is rotate. I'm going to tip it so that this comes forward, this goes back, and these guys more or less stay put. So, by the magic of PowerPoint, here we go. I'm rotating this up, that down. Now, at this point, you look at it and say, oh my goodness, this looks like a cyclohexane boat, doesn't it? It does. It's a boat. Now, what did we always do with boats? We always converted boats into chairs. To make this into a chair, we just need to grab the end here, move it down. So let's do that. Slowly moving this guy down until we get into a chair conformation. Looks like our lounge chair. Now finally, I'm a compulsive person sometimes. I really like my axial groups to be vertical. Makes it easier for me to see. So I'm just going to take and rotate the whole thing until my groups are vertical. Now, if you look at our two nitriles, we have one that is axial and one that is equatorial. 1, 2, axial equatorial is cis, isn't it? Another way to think about it, these are on the same side of our ring plane. So our stereochemistry has been preserved. Take-home lesson. The stereochemistry of the dienophile is always preserved. Cis would give cis, trans would give trans. Now let's do the legal disclaimer. We've drawn this as a beautiful chair. Right? But we all sit here and we realize this is a double bond back here, isn't it? It's not going to go into a chair, not willingly. In fact, it's going to look like this. But even if it does look like this on the back carbon, again, we can still say axial equatorial here and pick out our cis stereochemistry. Any questions? Well, here we use this dinitrile as our dienophile. Turns out that when you have electron withdrawing substituents on your dienophile, they react much, much better than simple ethene. Ethene is a very, very poor participant in a Diels-Alder. Here we have a carbonyl, another carbonyl, this is an ester, ketone aldehyde ester. All of these are good dienophiles. Here we simply have two carbonyls. There's our reactive group right here. Nice six-membered ring with two carbonyls. Either of these would react. And as we saw, we can put nitriles on them, and that works too. These are all very good dienophiles. This is really lousy. We could also do a 4+2 with a triple bond. The only difference here is we would wind up with a diene where our double bonds are opposite from each other, not conjugated. A very nice example of using a triple bond in a Diels-Alder type reaction is what's known as a 2+2+2 cycloaddition. So kind of like the breakfast. In a 2+2+2, we're going to take 3 moles of benzene. We're going to let these all kind of line up next to each other, and in one magical concerted swoop, we make benzene. It's long been known that benzene occurs deep underground. It occurred long before there was industrial pollution. Well, that's not where it came from. And they finally figured out that it was a simple 2+2+2 cycloaddition. The problem with benzene being deep underground is that it can slowly seep into groundwater. The classic example of that is very expensive Perrier drinking water. Back in the old days, they just had this deep well, and they pumped the water out, put it in little green bottles, and made a lot of money. Problem with that was that somebody analyzed it and said, my goodness, this has benzene in it. And benzene is now on the carcinogen list. Didn't used to be. When I was in graduate school, we used to wash our hands with it. Very good at getting stuff off. But now it's a hepatotoxin, can't touch it. So folks at Perrier had to devise a way to take their pure, unfiltered water and get the benzene out. So there's always a little bit in there. Any questions? Well, let's look at some examples here. Go ahead and do the products for these very simple 4+2 cycloadditions. Remember, carbons 1 and 4 on our diene are going to react with the 2 carbons of our dienophile. The bonds that we made here, these guys, again, if you look across the 6-membered ring, these are the 2 carbons of our diene. Same thing here, carbons 1 and 4, add to the 2 carbons of our dienophile. Our carboxylate ester just goes along for the ride. These are the 2 bonds we made. Oops. These are the two bonds we made. Again, look across the ring to find the dienophile. Aldehyde out here. Carbons 1 and 4, add to carbons 1 and 2. And the same thing if we have a ketone, 1, 4, to make this product. So making simple things like this is really very simple. Predicting the products. Remember, I'm going to ask you to do this backwards too. Okay? I'm going to look at something like this and say, what diene and what dienophile do you need? Remember what you do is just take it apart, find your double bond. These are the 2 carbons of the dienophile. These are the 4 of our diene. Now, one of the really neat things about the Diels-Alder reaction is that we can use interesting dienes and dienophiles. These get a little trickier to draw. But let's try it anyway. Whenever we use cyclopentadiene as our diene, we're going to wind up with a bridged product, aren't we? It's going to have this little CH2 sticking up in the middle. This is what it looks like. These are the carbons of our diene. These are the carbons of our dienophile. Now, if you have trouble seeing this, let's do it slowly. I'm going to take my diene, and even though I shouldn't, I'm going to grab the nose and just pull it out. When I do that, I can easily see carbons 1 and 4 are going to react with 1 and 2. When I do that, now it's simple to see what the product is. I look across the 6-membered ring to get the carbons of my dienophile. Now, you'll note that I put stereochemistry here on my nitrile. I have the nitrile pointing down. That's because this is virtually the only product you get. Here's the bonds we made, and this is pointing down, not up. Oops, this is referred to as the Endo isomer. The Endo isomer, you can think of it, if you will, as the group here on your dienophile is pointing into your 6-member ring. Endo into the ring. Now the other possibility would be this sticking up. That's called the Exo Isomer. Let's pretend that we have this as our dienophile. Here's our diene. We could get these 2 isomers. Endo, where the nitriles are down inside of the 6-membered ring, and the exo, where they're pointing up away from it. Once again, the endo is the only product that you get. Now, that might be surprising, but turns out that it makes great sense if you think about the mechanism in terms of the orbitals. What we're dealing with here is our diene. Here's our dienophile. And I've got them arranged this way. This way is going to give us the Endo isomer. The bonds we're going to make are those. Okay? Now remember, this reaction happens because we have p orbitals here reacting with p orbitals here. All right, so let's put in our p orbitals. These are the p orbitals of the dienophile. Up here on our diene, we have this set of p orbitals. We know that in order to make this compound, these guys, the ones in the back here, are just going to combine to make single bonds, leave these two as our double bond. Okay? Make sense? Remember, however, that we also have p orbitals on our carbonyls here, don't we? So if I put those in, they would look like this. What we have here is a great example of snuggling. The p orbitals here snuggle up with this pi system. They interact with each other. And that's better. The opposite would be if we had it looking like this. There's the p orbitals for here, p orbitals for that. Put in our p orbitals here. No snuggling. This would give us the exo isomer. The other one gives us Endo. Now actually it turns out that you don't need a pi system here for the snuggling to happen. If you just have a methyl group, it's still enough. It's still more stable to have the methyl group snuggle up with these p orbitals than to have nothing at all. It's just easier to see if you have something with no p orbitals. Any questions? Remember, the answer is always Endo. All right, let's get back here then. Well, this first one looks like it could be complicated, but of course it's not. We're simply going to take carbons 1 and 4 and react it with these dienophile carbons here. Look across your 6-membered ring. These are the carbons of the dienophile. Now the next one's a little trickier. The carbons of the diene that are going to react are going to be this one and this one, right? And they're going to react with these two. Yeah, that's the bonds made. Product here is going to look like this. Yeah. Really? Okay.
Oh, I know you're not playing.
How does
Just
it
trying to
look
see
like
if
this? Remember, we're reacting with this carbon and this one, and these two. So let's take and draw them out. Here's our diene. Here's our dienophile. It's going to come sit on top of it, isn't it? And the bonds we make are going to look like that. Therefore, this is our dienophile. Now the 6-membered ring that you look for to find it, remember, is this guy. 1, 2, 3, 4, 5, 6. So it's this one, not this one. This guy here is our 6-membered ring with our double bond. Any questions? All right. One more thing to think about in terms of cycloaddition. Here I have a simple dienophile, but I've put methyl groups on my diene. The stereochemistry of my methyl groups. If we trace the chain, we go this way, this way, this way. That's cis, isn't it? This other one, start here, go this, this, this. That's trans. So this is a cis-trans diene. Now what we're going to do is allow this to react. We're going to make our bond this way. And we're going to make a simple product. Now all I've done is put these bonds here and make them solid. Now remember when we had this series of slides and I took and I tipped the thing and made a boat? I'm going to do the same thing here, except I'm not going to show it to you. I'm going to do it all in one magical step. I'm just going to rotate the double bond down, rotate this up, and make my boat. Now if you look at it, you know that you've drawn the stereochemistry right here. Because look at this. Hydrogen methyl, hydrogen methyl. Hydrogen methyl, hydrogen methyl. So this is what your boat would look like. Now remember, we want to take the boat, take this in, jib it down, and make a chair. Again, let's make sure we have the right stereochemistry. Hydrogen methyl, hydrogen methyl. So that works. Now I want to tip it so that I get nice axial equatorials. Once again, hydrogen methyl, hydrogen methyl. So we've done it right. We wind up with a product where we have axial and axial. Those two are trans, aren't they? So on the back of our hand, let's write down, we had cis-trans, and we wound up with trans stereochemistry. What if we have trans-trans? Trans on this double bond, trans on that double bond. Same magic. We make our double bond, or make our 6-member ring. There's the bonds we just made. Rotate this down, this up, so we get our boat. Let's make sure we draw the boat right. This goes hydrogen methyl, methyl hydrogen. Well, it is right, but somehow I flipped it over. Sorry. Rotate it back, but it's right. 2 hydrogens on the same side, 2 methyls on the opposite sides. Rotate, carbon down, make a chair. Take the chair, straighten it up. We now wind up with 1 methyl equatorial and 1 axial. Remember from chapter 3, 1,4 axial equatorial is cis. They're on the same side of the ring plane. So, when we had cis trans, we got trans. When we had trans, we got cis. In fact, we can do a general rule. Rule simply says the same thing we did here. That is, cis trans, cis trans, trans, cis. Remember, the stereochemistry of our dienophile is always preserved. These two, cis would give cis, trans would give trans. So this allows us to do very complex problems, doesn't it? Let's just try one of them. Let's take this compound and predict our product. Now on an exam, I will give you one of these. But understanding everybody's art capabilities, I will probably give you a template to work from. I just ask you to fill in the methyl groups at the appropriate places. Let's do the easy one first. Our dienophile here is trans, correct? These 2 carbons in front here are the carbons of our dienophile. So we need to put methyl groups on there that are trans. We can make them both axial, or we can make them both equatorial. Equatorial more stable, so let's put them in as equatorial. Trans dienophile, trans product. So that's the easy one. Look at your diene. The diene here is trans, isn't it? Remember your rule. Trans gives cis. Now, we're dealing with this carbon and this carbon. We want to make them cis. So we need 1 methyl axial, 1 methyl equatorial. That would work.
Does it come up on Blackboard like this, Dr. Young?
I haven't written the questions yet.
No, on Blackboard, is it going to show up like this if I go to Blackboard
To review them.
to
Yeah.
review the lecture?
Oh yeah.
Pop up like something.
Yep, it'll all be there. All right. Let's go ahead and do one set backwards. Here are a set of final products. I would like you to draw the diene and dienophile that you would need to make this. All right, if we look here, here's our double bond. We want to look across to find the carbons of our dienophile. These are two 6-membered rings, aren't they? So we could say these were the carbons of the dienophile, or these were. This would be ethene. We know that that's really lousy, isn't it? Therefore, the best thing to do would be to say this was our dienophile, and these were the bonds that we made. Ethene is just lousy. You can make it work, but it's lousy. All right, so if these are the bonds that we made, then our dienophile simply had a double bond and the nitrile. Our diene here was a 6-membered ring, and there used to be a bond here and here. Our next one. Here's our 6-membered ring. Here's a double bond. We look across the ring to find our dienophile. Dienophile, a double bond, and the amide group. The diene. Well, we had these are the bonds we made right here. I'm sorry, let's pretend we just drew them there. Those are not the bonds we made. These are the bonds we made, sorry. This was a double bond, this was a double bond. Furan was our diene. These are the bonds we made right here. And our last one here, simple 6-membered ring. Look across the ring. These are the carbons of our dienophile. We have 2 nitrile groups. And what's their stereochemistry?
Equatorial.
They're both equatorial, which means they're trans. So, in our dienophile, our cyano groups were trans to each other. The rest of these carbons, the other 4 here, are simply from there it is. 1,3-butadiene. Trans-stereochemistry, trans-stereochemistry. Now with cycloaddition reactions, you can actually make some really neat looking compounds. Look at this one. Looks like it's complicated, doesn't it? But it's not. Find your 6-membered ring. That's this one. 1, 2, 3, 4, 5, 6. Look across. These were the carbons of your dienophile. So your dienophile had 1, 2, 3, 4, 5 carbons, 2 double bonds. The diene, well, that's this half. It has 1, 2, 3, 4, 5 carbons and 2 double bonds. This is simply 2 of these guys. One acts as the diene, the other as the dienophile. The next one is simple too. We have a bridge. So this pretty much, you come to recognize, I hope, means we're dealing with a cyclopentadiene, 1 carbon bridge. Our dienophile, double bond was here. Those are the bonds we made. And we simply have a ketone. Now, once again, this one looks really complicated, but here's our 6-membered ring. Look across the ring. These are the carbons of our dienophile. So this used to be a double bond right here. So our dienophile had a double bond, carbonyl, oxygen, carbonyl. Our diene had 2 double bonds through here and an oxygen bridging it. Just like this, except with an oxygen in it. Oh. All right, another very simple one. Here are our dienophile. Across the ring, we had a double bond here. What's the stereochemistry? Equatorial, equatorial, trans. Methyl group on one end, nitrile on the other. That was our dienophile. Our diene is simply butadiene. What if I put it, well, here's the butadiene. What if I put this way on an exam? This makes it even simpler, doesn't it? You look at this right away and you say our nitrile groups are cis to each other. So we have butadiene and we have cis nitriles on our diene file.
Too bad the pointer doesn't show up on the blackboard.
Well, you're right. It is too bad.
You have to bring a video camera.
All right. This one, a little more complicated. We look here first at our dienophile. We have axial equatorial. What is that? That's cis. Therefore, we have a cis dienophile. Our two methyl groups here are both equatorial. Now remember our rule. These are equatorial, that means they're trans. Where do we get trans? We got trans if we had cis strands in our diene. Now remember on the exam, you can bring a 3x5 card. And if you have trouble remembering things like trans, cis, trans, you can write that down very, very small in the corner.
This is for the methyl groups, right?
Yep. Well, whatever groups you have attached. So back here, we have trans, which means that our diene was cis trans. Somehow PowerPoint is giving me troubles. All right. We've been drawing these the same way over and over again. This is actually an old test question. I guess I was feeling grumpy. And so I put it in this way, just to make sure everybody remembered the operation. The operation is, find your double bond, look across the ring to find your diene file. This is equatorial, axial, same side, cis. The two carbons of our diene are going to be this one and this one. This one just has hydrogens, this has a methyl, so it doesn't really matter how you put it in, it would look like that. Let's do one more, and then we'll quit. Again, this was another test question. Look across our ring, find our dienophile. The cyanyl groups are cis to each other. These are the two carbons of our diene. These are carbons 1 and 4. Methyl group here is on one of the other carbons. So it's on carbon 2, and it would look like that. Any questions? Now there's 2 or 3 more examples at the end. I'm not going to go over those in class. You can work those, and then if you want to talk about it on Wednesday, if you have any questions, we can go over them. On Wednesday, we will do the nitration of, I forgot. But I'll send you an email. Okay. I forgot the actual lab, but it's the nitration lab. And that's because the following Monday, we're going to start talking about aromaticity, chapter 15, and then do electrophilic aromatic substitution. So Lab Wednesday is an example of electrophilic aromatic substitution. All right?
So we have until Wednesday to submit the other lab, right?
Sure.
Alright.
Can you do that?